of Technology. Austin Minnich is a professor in the Engineering and Applied Science department at Caltech. His research interests include low noise microwave amplifiers, quantum simulation on superconducting microwave systems. He received his bachelor's degree from UC Berkeley in 2006 and his doctorate degree from MIT in 2011, after which he joined the faculty of Caltech. Professor Minnich is the recipient of many awards, including the Office of Naval Research Director of Research Award, a Young Investigator Award, and also more recently, the 2019 Presidential Early Career Award for Scientists and Engineers. So it's a pleasure today to have Austin with us to deliver his presentation entitled Non-Unitary Dynamics of Spin Systems on Near-Term Quantum Hardware. Professor Minnich.
Thanks. Thanks very much for the nice introduction and for the invitation to speak. It's a great opportunity. As was mentioned, I'm going to talk about our recent efforts to simulate non-unitary dynamics with near-term quantum hardware. And just a little bit of introduction to our group. This is us as of maybe 1 or 2 years ago, and now we're about 8 graduate students, primarily in the Applied Physics department here at Caltech. And we have 2 main research directions. And we think of ourselves as primarily a hardware group and an experimental group. So one direction are low noise transistor microwave amplifiers that are used both for radio astronomy as well as for these superconducting microwave systems, specifically for qubit readout. And it was actually this line of research that got me into and interested in these superconducting microwave systems. And so the second direction of research is quantum simulation and applications of these superconducting microwave systems. And so today I'd like to talk to you about our recent work on the latter topic. I just wanted to acknowledge before we start that this was a collaborative work done in conjunction with Garnet Chan, my colleague at Caltech, Mario Mata, who was a former postdoc with Garnet and now is on staff at IBM. And the students who carried out this work were Xining Sun and Adrian Tan, who are graduate students in my group, as well as Ruslan, who's presently a postdoc with Garnet. All right, so like many of you, we are thinking about what we can do, what interesting problems we can tackle with near-term quantum hardware, where near-term is defined as where we have qubits on the order of tens, and more restrictively, the gate depth is on the order of essentially tens of 2-qubit gates. And so the questions that we and probably you are interested in are, can quantum simulations be useful in the near term given such constraints? And as experimentalists, we're also interested in what can we learn about the superconducting hardware from these simulations, and how can we use these types of simulations to drive the development of better hardware. Okay, so in that spirit, many people have been interested in and worked on algorithms for finding ground states. We know that finding ground states is a formally hard problem, so any algorithm is expected to be a heuristic and applicable in some cases, but not others. The most conceptually straightforward is, of course, phase estimation. But it's generally accepted that this circuit is too deep and too complicated for application on near-term devices. And so presently, there's been a lot of interest in this variational quantum eigensolver approach, where we parameterize a wave function by these parameters theta, and we can compute quantities on the quantum device, and we can use a classical device to optimize those parameters theta. So it has nice advantages that we can use shallow circuits. However, there's disadvantages that we need to specify in ansatz. We can get certainly some results from a shallow circuit, but they may not be very good. And finally, as the problem size gets bigger and bigger, the high dimensional classical optimization becomes non-trivial. Okay, so it's natural to ask some follow-up questions based on this present state of the art. Can we compute ground state properties without requiring an ansatz? Do we have to only compute ground state energies, or can we compute more general quantities for many-body systems like thermal averages, excitation spectra, dissipative system dynamics, and more on near-term devices. And we want to use these, primarily we're not advancing theory per se, but we'd like to understand the limits of today's quantum hardware and understand what we need to focus on as experimentalists to make this hardware better. So with that spirit, today I'd like to present three topics. So the first is quantum imaginary time evolution. And I know some of you are quite familiar with this algorithm, and for others, it may not be very familiar. So hopefully this is a good review for some of you and a good introduction for the others. Then I'd like to talk about some new work involving how we can use QITE to compute finite temperature excitation spectra and correlation functions. And finally, I'll end with how we can use the same algorithm to describe the real-time evolution of dissipative or open quantum systems. So first, just a review of imaginary time evolution and how QITE works. So suppose we have a problem specified by Hamiltonian given at the top left, and we'd like to compute, for instance, ground state or thermal averages, where the thermal average is given by the usual definition there at the lower left. Now, a common strategy for how to do that, classically, is to evolve the state in imaginary time. And by doing that, if you go to a very large beta inverse temperature, you'll eventually get to the ground state. And otherwise, you can use sampling methods to get thermal averages. So can we implement imaginary time evolution on a quantum computer? Well, there are methods that have been reported about how to do that. The most obvious one is to adapt variational approaches. And that was indeed done by Simon Benjamin and colleagues about 2 years ago. And this certainly works. Of course, you're still limited by the constraint variational approaches that you need in ansatz. And since then, and just in recent years, there's been a number of alternate schemes for how to compute thermal averages, not necessarily by imaginary time evolution. And they all certainly have advantages, and they certainly have drawbacks, just like all of these algorithms. So today, I would like to describe how QITE solves this problem. Well, and maybe solve is too strong a word. Maybe it addresses the problem. And in some cases, it's a useful algorithm. So the problem is this. So the actual operator that we want to apply to the register is in blue. And you because of course all the operators need to be unitary. We would like to approximate this blue operator with the red unitary operator if such a substitution is possible. Now initially, kind of intuitively, you would not expect that to be possible because the blue one is not unitary and the red one is. Now it turns out that it actually is possible to construct this operator. And the reasoning is as follows. So suppose you start from the top, state 1 in some initial state, and if you focus on the 2 red circles there, after imaginary time evolution, you get to state 2. And the key is that this is a normalized state obtained from imaginary time evolution. Now, if it turns out that the only states that changed substantially over imaginary time evolution are from red to blue, and the gray ones did not, then there's a theorem that tells us that these 2 states are in fact related by a unitary, which we just call U. And so this is the existence theorem that says there should be a unitary that links these 2 states. And so that's the key insight of this whole algorithm. So now that we know that there should be one for physically relevant states where correlations are bounded over some spatial extent, we just have to find it. So the way that you find it is you start with the blue operator, and you are trying to approximate it with the red operator that's unitary, and it operates over a slightly bigger neighborhood or number of sites than the blue one. So if you look at the equation just below the red operator, you expand your operator that you don't know yet in terms of coefficients x and polystrings sigma, and you're trying to make the action of this red operator mimic that of the blue one. And so you do that by minimizing the distance between the new state at delta 0, which is what the blue operator produces, and the state delta, which is produced by the red operator. And so this is a standard quadratic optimization problem, which unsurprisingly leads to a linear system. And the result is on the right there, and you don't have to worry about the details too much. The point is, if you perform tomography of all these different polystrings over the state that you're at, psi, you'll get the elements of the matrix and the vector, and you solve that on a classical computer to get the coefficients x. And so that gives you the unitary that best approximates the blue operator. So we can now put together this flow chart for QITE. We start in the computational basis. We can prepare a given state as we like. We then consider that we'd like to make this blue operator mimicked by a unitary one. So we do the appropriate measurements. We form the linear system, solve it on the classical computer, and we then have the coefficients. We apply them, and we get a new state, and that state then serves as the starting point for the next iteration of QITE. And you repeat this as long as you desire for the total length of beta that you would like. So if you continue this process until beta goes to infinity, you'd get to the ground state. Sometimes you might not want that. Sometimes you might instead like a thermal average of a certain operator. So it's known classically that there's sampling methods like metropolis sampling that allows you to get this type of average by sampling. The problem is on a quantum computer, there's not really a straightforward way to implement the rejection that underlies this metropolis sampling. There have been algorithms proposed as indicated at the bottom there. However, they are difficult or perhaps impossible to implement on a near-term device. It turns out that now that we can do imaginary time evolution, there is in fact another approach to get thermal averages. So this is this minimally entangled typical thermal states, METS algorithm that was introduced as a classical algorithm by Steve White in 2009. And it's, the main takeaway here is it's a Markov chain approach to sample thermally averaged observables. So the idea is you start with a state, which are the red circles at the top left. You evolve in imaginary time for some amount, and you can compute some expectation value, and that's one of your samples. You then measure to project onto a classical product state, and that measurement actually serves as the Markov chain step that ensures that you get the correct thermal statistics. So you collapse, and that provides your new classical product state to start for the next MET sample. And you do that. And it turns out if you do that around a few hundred times for the typical problems we've done, you get a good estimate of the thermal average. And there's no rejection step required. It's easy to implement, of course, both classically, but on a quantum computer, you just replace the imaginary time evolution by QITE. If you look carefully, you see QITE has replaced the imaginary time evolution on the two left figures. And that's all you need to do. And so this allows one to get thermal averages. So to finish up this section, to give you an idea of where we were as of about 1 year ago, we carried out experiments on quantum hardware, and specifically Righetti's Aspen quantum processing unit. And they have this layout that looks like this, and you choose a few qubits that look the best, and you carry out your calculations. And the results on the hardware are shown here. So the first plot is the energy or expectation value of the Hamiltonian versus beta. And the black line is the exact. And you can see on one qubit, you get a pretty good estimate of the right answer. And you kind of go under there because of readout error mitigation that we'll talk about later. You can do this for 2 sites, and the 2 different curves are just 2 different runs, and you do a bit worse, but you basically get the right trend. And this was basically the state of the art as of last year. The final thing, of course, you can do is this QMETS sampling. This was done for 1 site. And again, the trends are qualitatively correct, but quantitatively not particularly good. All right, so it's natural now to ask, can we simulate more spins, particularly getting thermal averages for more than just 1 site? And do we have to only compute this energy, or can we compute something else? And of course, correlation functions and other related quantities are a good way to get insight into many body systems. So we'd like to compute those. So that's what the next section will be about, is over the past 6 months, we've worked out how to compute correlation functions and excitation spectra at finite temperature for spin systems on 2 and 4 sites. So just a brief reminder about how to compute correlation functions. So this circuit was introduced about 20 years ago, and it's a way to compute the average of a correlation function u, v, subject to some initial state psi. So in this circuit, you have a system register, psi, and you have an ancilla qubit, and the H there is Hadamard. So in the way that we've set it up, you perform controlled operations with V and U controlled on the ancilla, and then you evolve in real time just on the system register. And if you do just a few lines of math, you'll figure out that if you measure X on the ancilla, you'll get the real part of this correlation function averaged over the initial state of the system. And if you measure Y, you'll get the imaginary part. So it's a pretty straightforward circuit. And this has actually been used in just recent years to compute correlation functions on hardware. So once you combine that circuit and the ideas I presented just a few slides ago for QMETS, it's actually quite straightforward to see how to compute finite temperature correlation functions. You simply add the QITE circuit in front of the correlation function, and you carry out METS. So in particular, you perform QITE starting from some state. You perform this correlation function circuit and measure. You then perform QITE again to collapse onto that classical product state that serves as the next step and then you compute the correlation function again. And you do that a few hundred times, and averaging over those samples gives you the thermal average of the correlation function. And just a brief technical note, it turns out that for the small system sizes here, it's actually faster just to explicitly perform the trace over the basis states of the qubits rather than do METS sampling. Because for instance, for 2 qubits, there's only 4 of them. So in this work, we actually did this trace evaluation rather than METS, but we have shown that both work. Now, this is clearly a more complicated circuit than what I showed you before as of last year. So if you have 2 sites, there's about 12 C0s per QITE step, which is somewhat manageable. But if you even go to 4 sites, there's 240 C0s per QITE step. And that's larger than the number of acceptable or feasible steps by about a factor of 5 to 10. So clearly we need some way to only include the non-redundant operators in QITE. And so that was something that Xining figured out over the past few months, is how to exploit symmetries in QITE and therefore reduce the number of operators. So just as an example, say we have a transverse field Ising model on 2 sites shown here, and it's easy to see that this Hamiltonian commutes with ZZ, and so it admits that Z symmetry. And that means that if you're doing quantum imaginary time evolution, the QITE operator should have the same symmetry. And you can use that constraint to reduce the number of QITE operators. So here's how. If you can start looking at the left side of the screen, you start with all 16 poly strings over the 2 qubits. And it turns out that because the starting state is real, and in this case, the Hamiltonian is real, quantum, or rather imaginary time evolution, the state produced by that will also always be real. And therefore, when you do QITE, you should similarly preserve a real state. And then it turns out, if you look at the action of these different polystrings, only those with an odd number of Y operators are acceptable under that requirement. So we go from 16 to 6. From there, you can exploit symmetries to remove all of those operators that do not commute with ZZ. And that leads you to these two operators. This is the third item from the left. And if you kind of know some group theory, this set is the normalizer of the symmetry group ZZ, those strings that commute with ZZ. Finally, it turns out that XY and YX in this example essentially have the same effect in the QITE operator. And so you don't need to include both, you just need to include one. And in the language of group theory, this is the quotient group of the normalizer with the symmetry group ZZ. So you end up with actually only needing one string, XY. And so clearly for D equals 2 with one of these discrete Z2 symmetries, you go from 16 to 6 to 1, which is a very nice improvement. If you go to a QITE neighborhood, meaning the support of that unitary, to D equals 4, with one symmetry, you go from 120 to 28 operators. And if you have two, as in the Heisenberg model, you go from 120 to 6. And it's not an exaggeration to say that these reductions are the reason you can even hope to carry out these calculations, because otherwise it's just too many operators and measurements and gates. Now, if you're pretty familiar with this field, you might know this tapering off qubits paper by Bravi and colleagues at IBM. And just very briefly, that scheme is related to the present scheme, but in their scheme, they use these symmetries to remove qubits. And it turns out that for the present problem, removing qubits can actually increase the size of the QITE domain D. And the cost of doing that is very substantial. So we found that it's actually better to keep the same number of qubits and reduce the number of strings. And so that's the approach that we've taken. All right, so we carried out these calculations on IBMQ, Pagoda, and Rome. And these are linear chains of 5 qubits with nearest neighbor interactions. And the single qubit error rates you can see are on the order of 0.1%. The C naughts are of order 1% or 2. And so let's start looking at some of the results. Here's a static correlation function on XX on sites 0 and 1, the thermal average of it versus beta. The exact curve is there in black, and the data that you get out of the quantum computer is in green. And you can see, again, you get basically the right trend, but the quantitative agreement is not particularly good. So we would like to use other strategies to improve the quantitative agreement of this result. And so there's two strategies we can use. One is post-selection, which is a fairly standard technique and which we need to adapt for the present simulation. So in this case, if a state has some known parity of that symmetry operator ZZ, then hopefully it's you can agree that that parity can't be changed by QITE, because QITE preserves the symmetry sector that the state is in. So if we start with a state with, say, parity +1 and we do QITE, we can check the parity at the end and make sure it's still +1. And of course, well, you can do this, but if you do that, then you're not measuring the polystring, which is the whole point of doing this calculation. So there have been a lot of papers recently which tell us how to measure simultaneous commuting polystrings. And the central idea is you include a Clifford circuit that looks really, it's exactly what's shown in that box, which allows you to measure the parity on the first qubit and the desired polystring on the second qubit simultaneously. So what we do in practice is we do that Clifford circuit at the end, measure each poly string in QITE, and those with the wrong parity are discarded. The second mitigation is also a well-known one, which is readout error mitigation. And the idea simply here is you prepare states in a known that are in a known state, and then you measure sometime later what they are, and you ideally would measure exactly what you prepared the state in, but of course due to readout error you don't always do that. So if you do this enough times, you can build up this matrix which will allow you in a statistical sense to correct for readout errors by applying the inverse of the matrix on the measurements that you actually take. So the next few slides are just showing the net effect of that. So we start with the raw. Readout error mitigation, you can see, makes a noticeable but a small but noticeable improvement. Post-selection, similarly, a small but noticeable improvement. And finally, combining the two largely eliminates the quantitative disagreement. So from now on, what I'm presenting is with both of these mitigation schemes applied. All right, now the final thing before we actually get to the real results are, it turns out for 2 qubits, you can do a lot of special simplifications. Namely, any 2-qubit gate can be written in terms of this single 2-qubit rotation gate, or specifically the QITE steps can be written in this way. And for real-time evolution, you can use this other type of decomposition. So the really special thing about 2 qubits is no matter what the value of beta and real-time you do, the circuit is of constant depth. And that is a particularly special feature of 2 qubits. All right, so let's see what we get. So we have a 2-site transverse field Ising model shown there. This is the energy versus imaginary time, as well as the static correlation function you saw before versus imaginary time. And for larger values of the coupling constant, it's, you can hopefully see from the Hamiltonian that it's favorable for the spins to anti-line. And so you see from the static correlation function on the right, you are exhibiting this anti-ferromagnetic order as beta gets bigger and you get to the lowest energy state. So that's an indication that the thermal physics is being incorporated. So now we can move on to more complicated things. So this is the real part of the ZZ dynamical correlation function on 2 sites. And the black is the exact and the orange is the hardware. And if you look closely, you can see you do pretty well at getting the right answer. You again have to keep in mind that regardless of the value of real time, it's a constant depth circuit. So that certainly helps a lot. For the imaginary time, similarly, you find a good agreement. Now, you can do the same thing, but compute at different values of beta. And these curves, if you look at them carefully, you can see there's some differences, but generally they look like a bunch of squiggles. And time domain data, when it looks like a bunch of squiggles, it's generally a useful thing to take a Fourier transform. And in the case of correlation functions, that has a deep theoretical meaning, which is that when you take a Fourier transform of these correlation functions, you get the excitation energies of the system as the poles of that function. So now all these calculations were done in real space, so you cannot quite interpret this as a dynamical structure factor, which is in reciprocal space for the wave vector also, but you still can interpret the peaks that you see as the excitations. So this is for beta equals 0.2, and you can see you have excitations at positive and negative frequencies, which corresponds to emission on the positive side and absorption on the negative side of excitations from the spin chain. And if you compare that to what you can just derive from the exact eigenvectors of the system, which you get a pretty decent agreement. So now we've turned these time domain waveforms into something that's a little bit easier to understand. So there's some discrete excitation energies of this spin chain. Now we can test a little bit better if the finite temperature physics has actually gotten into our simulation. So mainly what that means is that, for instance, excitation amplitudes should have a weight which is related to some type of Boltzmann factor in a partition function. So if you look at the left plot, this is for the amplitude of the ground state excitation. It should generally increase with beta because as beta goes bigger, temperature gets smaller, and so there's more population on the weight on the ground state. On the right side is the first excited state, and initially that population goes up as population shifts to lower energies, but as beta increases, it then loses weight to the ground state. And so if you take the amplitudes from the previous plot and put them on here, you actually get a pretty decent agreement. Not perfect, but pretty decent. The final check you can do is look at the emission-absorption ratio. So this, if you do the math out and derive it, you can figure out that the emission to absorption ratio is this Boltzmann type factor, and that's just reflecting as temperature gets low and beta gets big, there's no longer any excitations for absorption. So if you put that on a log plot, it should just be a straight line, and what you see is indeed it's basically a straight line. The discrepancies at higher values of beta are mainly because the absorption amplitude is sufficiently small that the various noise and uncertainties make the relative uncertainty of that value correspondingly bigger. So that leads to the discrepancies at higher beta. All right, so we now would like to extend this to 4 qubits. And as I mentioned before, for d equals 2, a QITE neighborhood size of 2, it's 12 c-naughts per QITE, which is for QITE step, which is not so bad. But for d equals 4, it's 50 plus c-naughts per QITE step. And that's really out of reach. What we have found is that getting acceptable results of the type I showed here, you're looking at most a few tens of c-naughts. Okay, so unfortunately in this case, we have to resort to alternate methods to reduce the circuit depth. And the method that we chose is circuit recompilation. So we start with the desired QITE circuit, which, as I've said, is going to be deep. And we try to find an equivalent circuit, or rather a circuit that can mimic up to some tolerance the action of QITE on a given state. So this is known as circuit recompilation. And for QITE, we use this base layer in red, which is just a set of single qubit operators, followed by these round A, round B, round A, 3 rounds. For real-time evolution, you do base layer plus 5, and you have a cost function where you maximize the overlap of these recompiled circuit with the original QITE one. Now, this scheme is in principle scalable in the sense if you do tomography to get the density matrix on, say, 4 qubits, there's nothing to stop you from doing that on a real system that could be bigger than 4 qubits and then recompiling just that section. So this is in principle a technique that could be used for larger systems. In this case, we applied it just for the 4 qubit system. Just to get an idea of the impact of that, so here's again this energy and static correlation function xx. So expanded just means the original QITE circuit with all the gates in it, and this is the recompiled. You can see that there's a noticeable improvement in this, and particularly for dynamical correlation functions, it's really essential to do the recompilation. All right, so these are the most complicated calculations we've done so far. So we have a dynamical correlation function on 4 sites. Again, we're plotting the real part and imaginary part of the ZZ correlation function. In this case, at a beta of 0.2, which is a limitation for 4 sites. And if you look at the top one first, you can see pretty decent agreement, although it's not quite as good as the 2-qubit case. And if you look at the bottom one, it doesn't really quite look as good. There's a systematic shift in the blue compared to the black. And we believe that the reason for this is ancilla decoherence. So remember that you have an ancilla and you're applying controlled gates on it, but while you're doing the real-time evolution on the system register, the ancilla qubit is just waiting around until you do the next operation. And it has time to decay into the state that it didn't start in. And that we have evidence for is the origin of this discrepancy. Now, fortunately, as others have done before us, as indicated in their papers at the bottom, we know that physically the imaginary part of the correlation function has to be 0 at time equals 0. And according to the way we've defined things, the ZZ correlation function, the real part, has to be 1. So therefore, you can do this phase and scale correction where you simply divide the data that you got by its value at time equals 0, and that has the effect of enforcing the requirement in the top equation. So if you do that, then you kind of restore the pretty good agreement for 4 sites. And so these, again, are the most complicated calculations that we have done. For 4 qubits, there's not as many tricks that you can play. And so the temperature that we can achieve is a relatively high one of beta as 0.2. All right, and then finally, you can take a Fourier transform just like this as before, and you can get the discrete excitations of this 4-site spin chain. And you can see you get a few more excitations. And in general, these are in pretty reasonable agreement with the exact result. And particularly the frequencies that you get are basically spot on with a little bit of discrepancy in the amplitudes. So just to sum up this section, I hope I've convinced you that finite temperature physics with 4 spins is indeed possible on near-term devices, although there's certainly some restrictions on how you do it and what values of temperature you can actually access. But you can, in fact, do finite temperature physics with these types of systems. All right, so in the last 5-10 minutes or so, I would just like to show a very new result that we're still in the middle of really fleshing out, but I thought it would be interesting to show the initial results, is non-unitary dynamics of dissipative spin systems. And this has been started and worked on by Hirsch, who I unfortunately neglected to put in the first part of the talk, but Hirsch is a new G2 student in my group who has started working on this. All right, so the whole part of the talk has been about QITE for imaginary time evolution. And of course, imaginary time evolution is in the title of QITE. So naturally, one would apply it for that. But generally, if you kind of generalize what QITE is doing, it's taking a non-unitary operator and it's showing how you can actually use a unitary one to show its evolution. So if you consider, we would like to consider how we might use the same idea for a more general problem. So if you consider the Ising model, again, we know, of course, it's unitary dynamics you can simulate on a quantum computer, no problem. Now, the dynamics of open systems are not unitary, but QITE is telling us that we can actually find unitary operators that will help us to simulate non-unitary evolution. So we'd like to determine if QITE can be useful for this more general problem. There's been a lot of prior work about how to simulate open quantum systems with these non-Hermitian Hamiltonians with quantum simulators and qubits. So there's schemes which range from representing the environment itself with qubits to using the natural decoherence of the actual simulator to harness that to simulate the system that we would like to study, and two variational methods to study the stochastic Schrodinger equation. So there's been a lot of different works, and they all, just like before, have their strengths and limitations. In the present problem, we would like to understand how to use QITE to solve for the dynamics of this master equation for a Markovian system. So the equation for the density matrix of a Markovian system in contact with some bath is what's shown here. You have a unitary part, but you also have this non-unitary part, which are encoded in these decay rates gamma and the Lindblad operators L. Some examples of these types of operators are spontaneous emission, where you lose a photon, sigma minus, or you can have an excitation from the bath, sigma plus. So you can turn this problem into one that's amenable to a quantum simulator by taking the density matrix and vectorizing it. And if you crunch the algebra, you'll end up with a master equation that is a Schrodinger-like master equation, or Schrodinger-like equation, excepting it has an anti-Hermitian term. And of course, that's the origin of the difficulty. Now, if you take that equation, of course, you can solve it algebraically or schematically as indicated. And if you want to actually practically solve it, you can trotterize it, and it will consist of two parts. You have the unitary part, where you have no trouble to simulate it, but you also have the non-unitary part, where we can attempt to use QITE to find an appropriate unitary operator to describe that portion. All right, so the quantum simulation, it appears for an open n-spin system, can be done by doubling the qubits to 2n to represent the density matrix, and by using quantum imaginary time evolution for this non-unitary part. And in this case, it's not really imaginary time evolution, it's just non-unitary evolution. So here's just some initial results from this example. We again take this transverse field Ising model. If you plug it into the master equation I showed before, it ends up looking something like this, where you have these Lindblad operators as indicated. And so the important point here is that if you have locality in the original system, which you do, because it consists of terms like ZZ next to each other, and you crunch that through the equations for the density matrix, all those terms that are local in the Hamiltonian and local as Lindblad operators remain local. And that's fantastic, because for QITE, it's really essential that the operators remain local for efficiency. So, so that will allow us to do this. So now, the last thing that we need to discuss is the starting state. So in order to do dynamics, we have to start the density.
Don't they remain local because of Markovian assumptions deriving the master equation?
I believe that is correct, yes. So it should be expected. Yeah, thanks. Yeah, thanks. So the last step here is we have to start the system in some state of the density matrix. So just supposing for the present example that we start with all spins up, and we want to see how the system evolves from that site. So the density matrix, it turns out corresponding to that is just a diagonal matrix with a single one at the entry indicated. And in the vectorized density matrix, that looks like what's shown here. Now, one should interpret this with a little bit of caution, because this is a noiseless numerical simulation for QITE, as well as the exact answer. So there's no types of imperfections associated with noise and gate errors. But it appears to work really very well, and we would like to make sure that it's amazing that it really does work so well. But the initial results, which were obtained relatively recently, indicate that this idea could actually work. So what I'm showing here is the average magnetization per site versus time, and the nearest neighbor correlation versus time. And the equations for those are at the tops of the plots. So this is an idea that appears promising, and so we're going to be investigating further and carrying out the actual simulations again, like we've done for the other correlation functions. All right, so that's the end of the talk. So just to summarize, hopefully I've shown that using this QITE algorithm, we can do a lot of calculations that previously would have been really quite complicated and perhaps out of reach for near-term devices. In particular, we can compute finite temperature dynamics, and that allows us to get excitation spectra of spin chains at finite temperature. And I've shown that there's appears to be a path to simulate more general non-unitary dynamics of open systems using the same algorithm. So if I could just finally conclude by revisiting the question, can quantum simulations on near-term hardware be useful? It depends, I suppose, on what one defines as useful. If we define it as learning something new about a physical system, it appears that that will be hard without error correction, because even with circuit recompilation, for 4 sites, we're rather limited in the imaginary times and so on that we're able to access. If we treat it as or if you define useful as indicating how well the hardware is performing and understanding the limitations of it and where we want to focus our efforts, then I believe that it's a very useful exercise. And for our particular studies, it leads to possible collaborations with some of your team involving hardware efficient error correction and analog quantum simulation, where the effects of gate error are not present. So finally, I'd like to thank the funding sources. So a lot of this was funded by a joint NSF grant with Garnet, me, and Fernando Brandau. The machine access was provided through a collaboration with IBM, and as well as interactions with Google. So again, I appreciate the opportunity to present, and I'm happy to take any questions. Thanks very much.
Thank you, Austin. So we clap for you virtually and physically.
Yeah, I'll imagine it. Yeah,
that's right. Well, you should see the little, there you go, see the little hands coming up. Good, the floor is open for questions.
So I have a question. So thank you for the talk, and like the results are really nice. Congrats on this. So did you try to simulate other systems than the Ising?
We have,
Heisenberg, I guess.
Sorry, say one more time.
Like the Heisenberg model, because like my understanding is like the QITE algorithm is also like more complex, like the more complex the Hamiltonian is, right?
Correct, yes. Yeah, we did actually in the paper that will go on the archive hopefully in the next week or so. We report calculations for the Heisenberg model. And the Heisenberg model is harder in one sense because there's more operators, as you say, but it also has 2 symmetries for rotations. And that helps counteract that. But I think it's fair to say that that model is a bit more challenging, but we do have results for it.
Okay, thank you.
Thanks.
Okay, other questions?
Yes, I didn't get totally the recompilation part.
Yes.
So how many CNOTs do you have at the end with this recompilation method?
Let's see. I passed it. Yes, so for 3 rounds, you're going to get 1, 2, 3, 4, 5. So it's 5 CNOTs per QITE step, and then 5, 6, 7, 8 CNOTs for the real-time evolution. So the total is you're ending up with around, call it 20 CNOTs total. And
okay.
Yeah, we found that much more than that, the results were just not particularly good.
Okay, yeah, thanks.
Okay. More questions for our speaker?
Hi, this is Jackie from Computing Sciences of Berkeley Lab. I know my question is going to diverge a little bit from your focus, but you mentioned that you also have some hardware work, which is on the amplifier design for quantum system. Could you just explain that a little bit?
Yeah, happy to. Yes. So essentially, the qubit readout, there's a lot of sequence of steps. So, and maybe you're familiar with this, but there's a readout resonator, and then you go to a parametric amplifier, which is pretty close to quantum limited. And after that, you go to an amplifier on the 4 Kelvin stage, which is a usually it's this high electron mobility transistor amplifier. And that's the amplifier that we've spent a lot of time looking at. And specifically, we're interested in understanding really the lower bound of noise figure that you can get in those amplifiers. And there's thermal considerations associated with that, because thermal noise is a key component of the noise actually at cryogenic temperatures. And there's also there's like material science issues associated with the quality of the epitaxy. There's noise associated with the heated electron gas as it goes through the channel. So our main aim, and we believe it's possible, is to get a noise figure from about 5 times the quantum limit to about 2 times the quantum limit. And our Google collaborators indicate that if you really did have such an amplifier, you could simplify the readout by removing these parametric amplifiers. And they are quite costly in terms of resources required to operate them. And so this is a step that it may be required to scale quantum computers to larger number of qubits. Yeah, I hope that answered the question, but feel free to follow up.
Yeah, just one pretty detailed question, just out of curiosity. In terms of dB, what is the goal for the noise figure?
You know, these amplifiers are so good that dB is it's small, but like a good amplifier you can buy from Low Noise Factory is like 1.5 Kelvin in the 4 to 8 gigahertz band. And we believe that we can get that to maybe 0.7 Kelvin. The quantum limit is about 0.3 Kelvin at 6 gigahertz. So you're talking about 2 times the quantum limit there.
Okay,
yeah.
Thank you.
Yeah.
Okay, very good. Other questions for Austin? So let me also ask a question. So on the last part, you had discussed the idea of this analog quantum simulation.
Yes.
So that may be a way to sort of stop this, or at least mitigate this requirement for very deep circuits in the digital domain.
Right.
If one considers atomic systems, Rydberg simulators, and the like, then of course, part of the challenge sometimes is to actually build in some kind of interaction between the sites or what have you. Are you also looking at sort of superconducting implementations for analog quantum simulation? Because there is a possibility to get larger numbers of qubits, but of course with much reduced wire count if we're not doing the usual digital gate sequences.
Yeah, I would say at the present time we are. I think your team and many people up there have made a lot of innovations with how to get all-to-all connectivity, and particularly with Roger and SpiderNet and others. So I think our focus now in that particular area is how to use that to, for instance, compute topological indices for 1D systems that could be having long-range interactions. So at that, we're not so much at the stage of designing alternate superconducting platforms at this point.
Okay, fair enough. Because I think one of the things we would like, and amongst others would like to do, is that the atomic approach has been, we can always do very good analog simulations. The interactions are very well controlled. The lifetimes are very long. Of course, if you want to do gates and turn off things, specifically on a pair of atoms or what have you, this is a bit challenging. So they have been branching out into more lattice-specific readout and control. Superconducting folks have always started off with, well, you can wire up everything. So you can control all of them, you can read all of them, but there's nothing that says we can remove some wires, right? And also get different variations and larger numbers of arrays. So we are certainly thinking about that also.
Yeah, I think of myself as a hardware person. It's certainly something I'm interested in, and my my background is mainly from the low noise amplifier side, so I'm still kind of wading into the superconducting side. So as time goes on, I'm interested in it, but presently I'm probably not the expert.
Okay, very good. Other questions for Austin?
Hello, this is Miro. I have a question. How hard is it to, or what are the major challenges to scale this from 4 qubits to 8 qubits?
Really, the 2 qubit gates have to be better. You know, if you have a few percent, you know, error in doing what you thought you were going to do compared to what you did, then you know, that adds up just so fast. So I think that's a major thing, and also the decoherence of the ancilla is a fairly serious problem, although as you saw, that can be corrected. But mainly what we saw is the circuits just quickly get so deep that there's really not much hope to get really great results out of it. That's the biggest challenge.
Okay, any final thoughts and questions for Austin? Okay, if not, we'd like to thank you, Austin, for spending your afternoon with us today, giving us a great talk on QITE. We look forward to seeing everyone at the next AQT colloquium, and we thank you and clap for you once more.
Yeah, thanks again for the invitation. I had a great time, and thanks for the questions.
Okay, everybody, stay safe and see you next time.